All right. Let's continue from where we left off last time. So we think of posterior sampling. So so what we started with this following motivation, that suppose we wanted to solve an inverse problem, meaning there is a measurement y, there's some signal x, you got some operator which is known with additive Gaussian noise C. Okay. Then you could formulate a least squares problem. So find an x consistent with this measurement y. And we saw that this problem can be thought of as a sampling problem. That's basically where we left off last time. Meaning, you can, if you, we went through this and said that, well, this problem if you especially want to regularize with a generative prior, leads to the following problem, that you want to sample from this distribution. Let P star be the original distribution of x, this unconditional distribution. What you want to do instead is to tilt it with an exponential exponent. The exponential is negative of the loss, or you could in general have some weight for alpha or 1 minus alpha, right? This is basically what where we were last time. Okay, we derived this and so on. So in more generally, if you have a problem where, say, there's some context y, okay, and there's an associated reward with this with Ry of x, okay, and now let's look at the following optimization problem. Find a distribution Q which maximizes the following. Consider a sample x from this distribution Q, maximize the reward Ry of x, maximize the reward Ry of x with some KL regularizer, meaning Q should be close to some base distribution P star and with some weight. Okay, where you see these kinds of problems, for example, if you're doing PPO or something like that, right? Ry of x has some advantage and some other things multiplied into it. But essentially, it's some weighted reward. You've got some reward. You want to find a distribution that maximizes the reward, but also is close to a base distribution. This actually is this is not exactly PPO, but PPO like instead of clipping. PPO has some clipping and all that stuff. But if you go back to Turpo or something like that, essentially that some approximations solve these kinds of things. Okay, then these problems are essentially the same as sampling from a tilted distribution, and the tilt is essentially then in this case there's no it's reward. So you got the base or the base distribution, and then there's an exponential tilt to it. And of course, you have to, this is just a proportionality, so you have to renormalize it by this. So the point of all this is that posterior sampling is actually a very useful thing to think about in several contexts. Either you're doing SFT and because of that for a model, you got a base model. You can either fine tune it for this thing, or you can do test time optimization that is given a single measurement. What do you do? All these kinds of things. Okay, so the machinery we are talking about here will be in the context of sampling, but of course has many other applications. Okay, that's all I wanted to say. So hopefully now the motivation is the problem we want to think about is clear. That I've given you a model which can sample from a base distribution P star, and I want to tilt it with some exponential tilt in general, and I want to sample from that. What are methods to do that? That's what we want to start, not just today's class, but the next several classes, we'll think about these kinds of things. Okay. So at a high level, there are two ways of thinking about these problems. First is whatever training-based, quote-unquote, direct approaches, where we either train or fine-tune a model for Q star, or the other option is sort of, quote-unquote, training-free approaches, or equivalently test time optimization, where we have access only to P star, and we have access to the measurement y, a single sample typically, and therefore you can compute Ly of x. If you give me an x, I can compute Ly of x, the loss for that y. And you want to tilt from this posterior distribution. Okay, that is P star e to the minus L, or e to the plus R, normalized by the thing. Fine. And we are going to look at sort of several different methods, including importance sampling, split Gibbs, rejection sampling, and approximations. That's sort of the plan. Okay, but very quickly, let me go through the direct approach. I'm not going to spend any time on it, but I just give you some literature on that. Direct approach is the following. So suppose I give you many samples of x comma y. Okay, then you can train for each value of y. You can train a new model P star of x given y. Okay. Yes, it's a conditional distribution, but you can also think of a conditional distribution as a parameterized by y and learn a whole family of models. Okay. And so you can always reduce posterior sampling. If you are given a lot of data, you can always reduce posterior sampling to a regular training the model, the same story which we discussed previously. And this can be sort of refined a little further as follows. Yeah. Where is Z? Yeah, okay, bad notation. Bad notation, thank you. Okay, I'm just saying that fix y as a parameter, not as a conditional. That's all I meant. I just wrote the wrong Z. Okay, yeah, thank you. Okay, and so you can refine this as follows. So if you are doing a diffusion model, you will need a score, and the score now is not of the unconditional score, but you want a conditional score of pt of x given y. Okay, and you can do Bayes rule on this. Pt of x given y is pt of y given x times pt of x divided by pt of y. So what do these three things mean? This one is, of course, the noise distribution. Okay. This one in words is saying, if I give you the noisy observation, how will the measurement look like? What we usually have a model for is the following. Let's go back to our motivation of this thing. If you have the clean sample, then what would the measurement look like is the following. It's through this particular thing. If you assume that the noise is Gaussian and you have access to this operator A, okay, then you know the distribution of P of y given x. Okay, it's just a Gaussian with the mean shifted by A of x, right? But in this case, you don't know this. This is a different object. This is the noisy version of x is given. It's not the clean version of x. So it's not clear what exactly this is. But we have a log gradient of the log, so we can just take question. Log, if you just expand the log out, you'll get the gradient of log of this plus the gradient of log of this minus the gradient of log of this. The gradient with respect to x. So this one goes away. Okay, which means that basically the conditional score can be written as the sum of two terms. The standard annealed score, because it's just grad log pt of xt, and there's a grad log pt of y given xt, which is the measurement based guidance. Okay, meaning you are at some noisy xt and the y is guiding you in that direction. Now, we don't know what this is, so you could essentially just try to train a model to do this. And right, instead of learning the whole distribution, you could try to fine tune. You have this base model, you could change the architecture in some manner to incorporate this and fine tune, or learn this separately and add it. There are a whole bunch of things you could do. Yes. Yeah. And X is an image we are generating, right? And this is my prototypical example in my brain. Right? So we are doing, so PT is a diffusion model that generates an image. PT is a diffusion model that just generates images, unconditional, no text guidance. Yeah. Okay, so it's a null text. So good. I was just going to talk about what it means in terms of text conditioning. Okay, so intuitively, the basic unconditional this thing, if you look at it this way, it says that it just guides you towards a manifold of images, whatever it is, generically. That is one PT of y given xt. Like, that's not something that a model can generate. Good. It cannot. So we are not doing training. I'm talking still about training-based methods, not training-free methods. Yeah. Okay. So in the training-based methods, you need to train such a model. So how do you do this kind of a model? How do you train a model to do text-guided thing? This combination. That's your question, correct? Right. So let's original model. It could be a classifier, for example. So I could just basically say that y is one of 10 different things. Okay, it's categorical, and then I could just say what's the I want pt of 1 given xt. Huh.
suppose my text input is like a flip embedding on the text, right? And then, like that's an input in addition to, the diffusion inputs at every time.
Correct.
Right? So in every denoising step, it's going to take the diffuse output plus.
I see.
Right? Now,
Good. In that case, this is not very, thinking about it the way I talked about it is not super meaningful for the following reason. You don't have a measurement operator that takes an image and gives you a text with additional Gaussian noise. So here really my mental model is that I have got a noisy image. So even though I didn't say it, that's the mental model. I have a noisy image or partial image or a blurred image, and I want to, I have a measurement operator, and then I can fine tune a model for these kinds of things. That's my mental model. How do I do text guided image? How your question is, how does this fit with a text guided story? Okay.
Yeah, your answer is, this does not fit the text.
It doesn't, because Litu, you wanted to say something?
Yeah, the text you pass it through click, you have a click embeddings that you can think of y as that. Yeah, now x0 will be an image that you can generate from xt. Yeah. So when you pass that x0 through your image encoder, you will be in the same space as y. So then you can just compute everything in your data. Right? Because so you need a separate thing.
You need some A to translate between these things. No, but it was never PT. But that was never PT before. No. The map from X to Y was this. In that running example, here is the map from X to Y. Your PT is all our densities, but you wanted to know, if I give an X, how do I get a Y? Is it making sense?
Yeah.
Okay. But nevertheless, now coming back to how so for text guided things, the way you train is through text dropout. You look at this X comma Y setting and train a single model, find an embedding, a Y called null text, no text. Okay, and then once you have that, you can instead of training two separate models, you just train with, sometimes you put in null, sometimes you don't put in. It is just a bunch of models of model parameterized by X comma Y. Okay, with PT. And that's all there is to it. And then how you use it, once you have this model, you can do classified free guidance or whatever else you want to deal with it. Okay. But this is the training-based methods. And what I want to focus on in this is mostly tilting during runtime. This meaning I have a base model of just P star of X, and then, or PT or P star or whatever, some way to sample from P star, and I want to sample from P star e to the minus some reward of y or loss of y. But that implicitly assumes I have a model that can translate from X to Y spaces, that A model. And how that translation could be stochastic because it's a noisy addition or whatever. And because of, if it's stochastic, then it actually gets a distribution there as opposed to a delta function. Okay. So on the mental model I'm actually running through whenever I'm talking about any of it is that model. Okay. That operator, typically A, for many of these things is a learned operator. You can and you usually can backprop through that operator through. So, but to go through, to talk about this training-based methods, I've put some references. I'm not really going to spend too much time talking about it, but it's there in the notes. So you can actually look at these papers and see. In particular, this Jonathan Ho and Saliman's paper on classified free guidance, where you train with this mix with text dropout and so. It's very well known. And I also like Sandra Dielman's blog. It's actually a very comprehensive blog. It's worth reading for just a great survey. All right, so the bulk of the class is on training-free approaches, meaning I have access to either P star of X or grad log PT of X, and I want to sample from the tilted distribution. Okay. So first, the simplest way of thinking about this is just going back to basic rejection sampling. Okay, what do you mean by that? For simpler, so I will, for just concreteness, I will have it in the reward tilted thing. Meaning, for some y, I have a reward ry of x. Okay, and I want to sample from e to the ry of x times p star of x, normalized by the partition. Okay. And I'll also further assume for this discussion that the reward is non-negative and bounded between 0 and R max. Okay. Some of this can be generalized, but this makes life much easier for me to just talk about with these bounds. Okay. So now first, so this is the distribution you want to sample from, right? E to the R divided P star divided by Z, capital Z, where Z is a partition function, meaning is a normalizing constant, is the integral of the numerator such that this Q star actually becomes a density function. First, because we are assuming R is bounded between 0 and R max, then you see that this integral is at least 1. Because e to the R0 with R0 equal to 0, this is 1. And this is, yeah, okay, there's whatever. So Z is at least 1. And therefore, we know that Q star is bounded by e to the Ry of x P star, which is further bounded by e to the R max times P star, trivially. Okay. So let's call M is e to the R max. Then you see that Q star by P star is bounded by M. We are now in the setting of lecture 1 rejection sampling. Okay, what are we saying? What was rejection sampling? Well, suppose I have samples from a base. The story of rejection sampling was the following. I have access to a sampler from P. I want to sample from some other Q, and I know that Q is no more than M times P for any X. Okay, then how do I generate samples from Q? That was the rejection sampling box which we talked about in lecture 1. So now we are in that setting. There's Q is less than M times P. And so what would you do? You would first generate a sample from P star. You would also now sample an independent uniform, okay, independent of anything else. And then accept this sample X if it happens that U is bounded by Q star by M times P star. Okay, this is something you can compute because X has been sampled. It's a test you do. This X and U is known. This is an acceptance step. Else reject the sample. Equivalently, the same thing can be thought of as the following, what I described. There is you compute so this test of acceptance is simply indicator of whether this uniform is less than Q star by MP star of X. These are the samples, X and U, which is the same as choose an A, which is Bernoulli, just 0 or 1, and the parameter, the probability of success of the Bernoulli is simply e to the Ry of x minus R max. Okay, it's exactly the same thing. And then Q star of x is simply the conditional probability of P star given A equal to 1. So this gives you the first algorithm for just as rejection. If I have a black box P star sampler and I have a single measurement y, okay, and I want to generate a sample that's consistent with that measurement y, I just repeatedly sample from P star, and for each time, so I generate a sample x1. Then I generate A1 associated with it. Meaning, how do I do that? I sample a Bernoulli with parameter e to the Ry of x minus R max. I put in whatever that x is there, and just that will give me some probability. And if that happens to be 1, then I say that this sample is indeed a sample from the correct distribution, else resample. Okay. So this is a valid algorithm for based on just, it's a single sample of y, but will require potentially many samples of x, because you need to resample till it's accepted. And this can be really bad because Ry of x minus R max, there's an exponential there. And depending on how it is, these probabilities could be tiny. Okay. In fact, and typically this will have some bad dimensional dependence. And in general, we know posterior sampling is hard. Okay, it's exponential in dimension. So, which means that there must be instances for these kinds of things, so that you'll require extremely large. Most samples are going to be 0 essentially, and you have to do this many times before you can get this. But at least this is one concrete method where just to set the yeah. In fact, this is just as a side thing, which is why you can think of RL and things like that as some rejection sampling. You can, if you want to think about these kinds of things in test time, if you're trying to do PPO or some things like that in RL. You can think of it as a sampling problem because of this connection. Essentially, just a rejection. You can think of it as a rejection sampling because of this. Yeah. All right. But this is your basic method. But we'll talk about other things which people are doing as well. But is there a question, Sujay? No, it's okay. All right. The next thing you could do is, if you don't want to reject samples, you could try an iterative procedure. The iterative procedure for this would be split Gibbs sampling. What is a split Gibbs sampler? So first, let me talk about the references which I'm using for this. So there are a whole bunch of split Gibbs samplers. I'm going to give you, I'll talk about what it is. It's all these papers 2, 3, 4, 5, 2, 3, 4, 5. For some parts of it, I will use the papers 2 and 5. For other parts, I'll be focusing on paper number 3. But there are a bunch of problems which do this thing. So what exactly is this method? Yes. On which one?
You have your unmodified thing.
Mm-hmm.
Generating from it is accepted.
Yes. That's all. That's it. Of course. These algorithms, this algorithm is inefficient. In fact, I think, it's exponentially bad in dimension.
Of a laughing cat.
Yeah.
Have something that generates
Exactly. Exactly. I think that's the simplest thing. You want a picture of a laughing cat. You say, forget the laughing cat. You generate a picture and see if it has a laughing cat. If not, resubmit. That's essentially what rejection sampling is. Just do this until you get a laughing cat. Okay? I'm not guiding it in any way. I'm not guiding the sampler in any way. I'm
saying it's possible.
All I'm saying is that this is possible. I'm just making a connection. I'm not saying this is a useful algorithm in any way. Okay, these things could work in low dimensions. Okay, but as dimension go, I mean, if you want, yeah, that's all. So a second one, if you don't want to just go on rejecting till you get something, is split Gibbs sampling. So what is split Gibbs sampling? Okay, what is Gibbs sampling? Let's think about Gibbs sampling. Going back to book. Okay. We talk about in the multi-dimensional exercise, but let's just talk about. Suppose I have a density Q of 2 variables x and z. Okay, then suppose that you had black boxes. I want to sample from this. But instead, I have 2 black boxes, one that can sample from this and one that can sample from this. Suppose I had such a thing. We'll connect it to our problem in a minute. But I'm just recalling what rejection sampling, what Gibbs sampling was. Okay. So meaning I can sample from x given z and q of z given x. Then how would you generate a sample which is consistent with both the distributions? Then the Gibbs sampler was essentially the following algorithm. Initialize with some x0. First, you sample z1 from q of z given x0. So you have this black box, so you can generate a sample from this black box. So I got xz1. Then freeze z1, feed it in, and sample x1, which is q of x given z1. Then go back and iterate and use this x1 and generate a z2. Use that z2 and generate an x2. And just oscillate, go back and forth. Constantine? So, okay, let me restart. I want to generate a sample from the joint distribution x comma z. So I need a pair of samples x and z, both which are consistent, which come from Q. Okay. There is no guidance. This has nothing to do with guidance. That's why I want to step this x and z. X is neither image nor guidance. I've just made up 2 variables. Maybe I shouldn't have even called it x and z. It's some alpha and beta. I don't know. Some 2 variables I want to sample from the joint distribution. And suppose I have black boxes which are conditional samplers. I don't still know the connection between this and the problem we're talking about, but I'm just talking about in the abstract. Okay, I have a black box which can sample from q of x given z, and I have another black box that can sample from q of z given x. And I want to get a pair x comma z, which is consistent and from this joint distribution q of x comma z. Then what Gibbs sampling said is the following. just alternate. First pick a sample initially with any x0. Okay. First generate a z1 from this particular marginal sampler, conditional marginal sampler. Use that sample and feed it in and generate a new x1, which is from the other marginal conditional sampler, and then alternate between these two. Then eventually xi zi will converge to x comma z, which is a sample from this joint distribution x comma z. That's all I'm saying. The connection to our measurements or all that is all unclear at this point. But I'm just telling you what, if I wanted to generate a pair of samples which are from joint, I can do it through just alternating between conditional samplers. This is lecture 1. This is what we, and the way we proved this is we showed that this is a special case of, this is a Metropolis Hastert with no 100% acceptance. We reformulated this as saying, this is nothing but the standard Metropolis Hastings algorithm, but which is set up such that you always accept. Okay, and so it's a Markov chain, and then this Markov. So this convergence depends on the mixing time of that Markov chain, and again, therefore, it could take a long time for this to happen. Okay, but this is a valid method to generate this pair of samples. You had a question?
No, that's it.
Yeah, okay. That's basically the proof mechanism for that. So at this point, it's still not clear what the connection is to anything we are talking about now, but I'm just recalling Gibbs sampling. That's all. Note that second point. Note that the above also immediately applies if x was not a scalar but a vector in Rd and z was a vector in Rp, d and p being some arbitrary dimensions, and I had boxes which could sample from these appropriate joint conditionals. Okay, q of x given z and q of z given x. Exactly the same kind of thing goes through. So what? Well, let's now think about split Gibbs. So this goes back to split Gibbs for the following. I want to sample here from p star x given y is proportional to p star of x e to the minus ly of x. This is what I want to sample from. Okay, that's our measurement loss tilted sampling. More generally, I would maybe want to sample from p star of x times p star of y given x. Why? Because what generally I want is a conditional sampler, p star of x given y. From Bayes' rule, it's proportional to p star of x times p star of y given x because the normalizing constant is whatever it is. It's not y dependent, so it's just some normalizing constant. Okay. No, it is y dependent. Right, wait. Let me see. P star of x, p star of y given x. Yeah, p star of y. It's not x dependent. Sorry, that's what I meant. It is only y dependent, but so it's just a normalizing constant. Remember, we are in the setting where I give you a single y. Okay, and you have this box which can sample from x, and I want to get a sample that's of in x tilde which is consistent with this y. All right. So to do this, let's introduce a new variable z and just say it's identically equal to x. Okay, just set z equal to x. Then the joint distribution of x and z is p star of x comma z given y. What is that? Well, that is because x equal to z, it is whatever the density we had previously, p star of x e to the minus L, normalized appropriately, times a delta function at x equal to z. Because we haven't done anything fancy, we just said z equal to x. So this joint distribution in the xy space lies on a line, on the x equal to z line. Once you have got an x, z is known, so this is a delta function there. Y is fixed, here's the loss. What do you mean?
No, but you're saying you're getting a pair x, comma z. Are
Yeah.
you saying x is sampled from the original distribution or x given y? On the left side.
Here, that's why I've written it out. Okay, this is the density. So what I mean by this is that's why I've defined what p star xy x comma z given y is there. It is the conditional is the tilted distribution of p star with y times a delta function, which is just making sure that I get a sample of z for free, essentially, once I've sampled x. Okay. Now let's relax this hard constraint, z equal to x. Okay. by some temperature or rho. So instead of making the delta function of z equal to x is relaxed to e to the minus 1 over rho x minus z whole square, okay, for some rho greater than 0. So we see that if rho equal to 0, this becomes a delta function effectively. But for any rho not equal to 0, it's a softening of this delta constraint. Okay. And so once you do this, then the relaxed sampling problem is the following. Instead of sampling from x, z, from the conditional p of x comma z given y, we'll sample from q rho of x comma z given y, where q rho is defined as the following. We had the same thing previously. P star of x, e to the minus ly, normalized appropriately, but multiplied instead of the delta function by this exponential. It's just a softened constraint. Yes?
Think of then C as a normal with mean x and some variance rho by 2 or conditioned on x.
And y? Or what? Did this?
Like you're relaxing the delta.
I'm not. So you are
Was a e power minus 1 by rho sub that matters.
correct, but so you're saying I will just do. You're saying this. It's a conditional distribution. So you could, but I'm not going to use that interpretation at this point. Okay, all I'm saying is there's a softening of the constraint, and some renormalization is going to happen because of this. Maybe there's some other constant. Then if my notes are wrong, I'll just pull that into z y of z prime of y, something else. Okay, so that this again a valid. All I want this to be a valid distribution. I don't think this integrates to 1 this way. So let's just fix it. Okay, something else. Okay, this is my valid distribution at this point. So now we will do the following thing. Let us define x given z for this one. Now let's look at this distribution. What is this distribution? Now I'm going to think of y as just a parameter because there's just a single y. There are two parameters in this problem. There's a y and there's a rho. There are these two parameters. So let's look at q of x given z with y and rho treated as parameters. So when y and rho are treated as parameters, x given z means this depends on x and this depends on x. These are the only two terms here that depend on x. We have put that. The rest can be pulled into a normalizing constant. Okay. Similarly, z given x. So this depends on z, this depends on z. This can be pulled into a normalizing constant. So therefore, we have two distributions, q of x given z and q of z given x for a fixed rho and y. Okay. Suppose we had a black box that could sample from each one of these things. Then I could alternate between these two to get a sample from this. And then further, I could come up with a schedule of rho going down, right, to actually get a sample from, approximate sample from q0 x, y, z, which is exactly what we want. This is split Gibbs sampling. Okay. I've just described the box. Now we need to talk about how each one of these boxes are built. But hopefully the method is clear. Okay. You first introduce a dummy variable, z equal to x, and then relax that constraint. Intuitively, what are you trying to do? This one is trying to sample from some, to be consistent with the distribution of images, if x is what is an image. This one is just trying to be consistent with the distribution with the measurement. It doesn't care whether it's an image or not. And you're alternating between these two, saying, I want consistency with image, consistency with measurement, and going between these two to actually get to the right one. This rho is allowing some flexibility so that there's no hard constraint. It's a soft constraint, which is sort of alternating between these two, getting it. That's the intuition for split Gibbs. But now you can see that this will converge as well. Okay.
X is a high likely sample and B is a high reward sample.
Correct. Yeah.
And you want to treat that both.
That's right. You want to measure. There are two manifolds. There's a manifold of measurements and a manifold of images. You're sort of sampling alternately from each other, using the previous sample as an anchor to get the next sample. You're tilting it. That's basically what is going on. Okay. But you can see that now you see the connection to Gibbs sampling. It is just Gibbs sampling. If rho equal to 0, then it will collapse when X and Z are equal to each other, you're forcing both constraints to be satisfied simultaneously. For some small value of rho, you're allowing some softening of this constraint.
If I had a score for P, I could place sampling with like gradient steps in both directions.
But this is not P, so neither of them is a score for P. There's still some difficulty. Let's talk about, we'll get to the algorithm. So Constantine's question is that if I know how to sample from P, is it immediate that we'll get any one of these things? Not yet, because the first step does not require a sample from P. It requires a sample from a particular exponentially Gaussian tilted P.
That intuition that you said, if I had to score,
Uh-huh.
I could see wherever I am and take a gradient step that increases the score.
Uh-huh.
Then I definitely can take the derivative of the loss. I can take a
Gradient step in terms of the loss.
That's alternating.
Yes, exactly. That's essentially it. Precisely.
That's small.
It's essentially the same thing. What you're saying is exactly what is going to happen. Okay. What you're going to do is you're going to use the score and take a step with this one. So there are multiple things. This is saying you go all the way. What you're saying is I don't go all the way. I just take one step each. Do you see the difference?
Oh,
This algorithm, it is, right? You're anchoring on Z and you're getting a true sample from X. You're saying, but you're doing even less. Okay, but I'll come to what you're talking about. Yours is yet another variant of this. It is a single sample approximation of this. But I'll first talk through this and then I'll come back and address your question. Okay. So this algorithm says I sample from this box, I sample from this box, and I'll get a guarantee. Okay, and so you also need a way to schedule some cooling schedule to how rho is going to go to 0 so that I can get provably correct sampling from P star of X given Y. Okay, that's really where we are going with all this. To do that though, we need a way to sample from these two boxes. Okay, so up to this point, there are several papers which have discussed this kind of method going. I think the earliest paper I saw for this specific problem is sort of mid 2015 or 2016. Though, of course, this kind of split gives goes back decades. Okay, in this context, that is sort of the earliest paper. That's 2. But the paper I'm going to talk about, this specific method, is from 3, which is about 2022-23. So let's look at this, the first one. It is P star with e to the minus 1 over rho x minus z whole square. Z is fixed here. Now, so therefore you can think of this as if you think of so now going back to your interpretation of noising, it is just Gaussian. This is nothing but, you can think of this. Suppose I had an X star and I just added noise to a certain noise level, that would be the distribution. Okay, this is just an observation, right? Because X star, if I had a certain X star and added noise to it, then the distribution of Z will be it's a convolution which will, and for any given X star, the conditional distribution will just be an X star shifted noise. X star would be the new mean and you'll just get Gaussian around it. Which means you can think of that as the forward process or the OU process. You start from an X star, and what would have happened because of an OU process, the conditional distribution at some point in time, at some specific point in time. Does it make sense what I'm saying? And therefore, once you make that observation, to actually sample from the first step now is very easy. We can use the standard DDIM process if I initialize at a specific time, because there's a immediate relation between variance and time. Okay, you choose the time correctly so that the variance at that time is rho essentially, and then you put the initial condition as Z, and if you just run the DDIM backwards, that's a sampler from Q of dot given Z. Okay, this is just an observation once you just look at this thing, and this is so DDIM samplers give you the first step for free essentially if you have a DDIM sampler. So you can get this sampler using just DDPM, DDIM, whatever, whichever you want. You want ODE or any of these annealed samplers are going to give you the first step. And for the second step, This has nothing to do with P star. It is sampling from this. Okay, so there's some loss function. Hopefully it's smooth. It's regularized by some z minus x whole square. So it's strongly convex, hopefully. So I should be able to do Langevin dynamics for this and use all the machinery we do to get fast sampling from this. Okay, because it's a strongly convex function. If L is nice enough, then you're in business. Okay, but the problem is we have to discretize this. You have Langevin Monte Carlo. You have a sampling error. So I need to fix it. So I'll do Mala. Okay, meaning Metropolis adjusted Langevin. What is that? Use the Langevin Monte Carlo as a proposer and the Metropolis Hastings as a access selector. And if you do that, that's a way to unbias. So I don't remember whether I made this point some time back, but in LMC, we saw there's a bias for LMC with respect to LD. This bias can be removed by just using Metropolis Hastings on top of a Langevin dynamic, LMC. Okay, use Metropolis Hastings as just an accept rejector. Okay, and use this as a proposer. Okay, so this algorithm is called Mala, Metropolis adjusted Langevin, and so you can just use Mala to actually sample from this. And so the split Gibbs sampler will asymptotically converge if rho is scheduled appropriately, but there are limited guarantees on how many steps. Again, in this case, it's going to be exponential in dimension in general. There is no free lunch, whatever you do, because fundamentally this problem is hard. Okay, I'll talk about that a couple of weeks from now on what kind of theory is known on these kinds of things. Right? But at least for this, and if you want to read more about the proofs of this, but under some conditions you can get poly D if the functions are nice and so on. But I've deferred to those references, specifically paper number 3 by this is by UJ's group. UJHE. She was at CMU, now at Yale. But this is the paper I'm talking about for this last piece. But this way of sort of thinking about a split Gibbs, I think goes back even before. These people were working on this in 2018, then there's a 23 paper. There's a whole line of work on sort of thinking about it. But this particular algorithm, the guarantees, goes back to what this particular paper by Xu and Chi from 24. Now, coming back to Constantine's question. So this one is running 2 algorithms, both to all the way to completion. Okay. Agreed that each one is in general not hard, meaning one is because you just run a DDPM for for an appropriate number of steps, where the number of steps depends on the rho parameter. As rho is sort of changed, you get closer and closer to fewer and fewer number of steps. The other requires a Mala, which has you need to sample from that. So instead, what you are suggesting is just skip the first. Instead of running the DDPM all the way, I just take one step of the DDPM, essentially, and then alternate. People have done these kinds of things. I don't know what guarantees are. I don't think there are any guarantee. As far as I know, there are no theoretical guarantees of any of these kinds of things. Meaning, instead of actually sampling from these two, the more the formal way of saying what you're saying is that just take one step. You have a method which will take many steps. I'm just going to take one step in each one and just alternate between them. Will that converge? I don't think it has been shown. Maybe other people here know that, but as far as I know, there's no theory showing anything. But that algorithm people have sort of talked about, but as just a heuristic. Okay. And I think that is even more broad, going beyond this DDPM, DDIM, and image sampling. People have thought about split Gibbs in other contexts, but I don't think there is an understanding of what happens when you don't actually sample from any of these things, but just go part of the way and just iterate between this. Will this actually converge? I don't think there is theory known for that. But yeah. Is that, yeah. Okay, so this is method number 2. Let's do method number 3. By the way, I'm going to talk about a bunch of methods today, none of which work well in practice at scale. Okay, we will get to practice in some time. So you have to give up either theoretical guarantees or scaling. Okay, all these things have bad scaling, but it's useful to think through it because it tells you how you can start thinking about these problems at least. Okay. They work, okay, I should be a little bit more careful. They don't work in practice at 3 million dimension scale, which is the image dimension. At smaller scales, for example, if you go to sort of a sampling, so many people in mechanical engineering and fluids, people are talk about 10, 15 dimensions, in which case then all these things are actually reasonable algorithms to think about. Okay, and there are a lot of people who have thought about these things in those settings, but much lower physics-inspired, much lower dimensional spaces is what those communities care about. Third is sort of importance sampling or test time Monte Carlo. Okay, so what we want is this. Okay, we are just going back to the same problem. We need grad log pt of xt given y. Okay, so what we are going to show, so I want to thank Advait for this calculation, is that it can be written in this way. This kind of calculation is known in other settings. This particular way of writing it, I just got from Advait, so I'm sure these ideas are sort of there in literature and other spaces as well. So that's why there's not a published paper or anything. It's just sort of something it's written up here. What is this saying? It says grad log pt of x given y, which is what we care about. This is the conditional score, can be written as the ratio of two expectations. The first expectation is p of y given x0. So x0 is the true image distribution, xt is the noisy image, y is the measurement. So it can be written as the expected value of x0 minus xt by sigma t square, okay, times p of y given x0, and the other denominator is just the expected value of p of y given x0. Okay, what does this mean? Before I expand, let's reverse engineer this. First, DDPM or DDIM gives you samples of this, right? You know the distribution of x0 given xt. That's what it's sampling from, meaning I start at some noise level t, run one trajectory of any of these algorithms, it'll give you a sample of x0 from this conditional distribution. That's what that box gives us. Okay, so I can draw n samples of that from that x01 through x0n. So these are not the true prior samples. These are this particular tilted samples, because the true prior is this. Okay, that's not what I'm saying. We will only start at a particular time t, then we will get this sample. So xt is given any xt and just running for t steps. This is what the DDPM sampler is going to give us. Good so far? Okay. So suppose I have these samples. Then these expectations can be just approximated by Monte Carlo estimates from samples. So the numerator expectation is can be written as this integral and this speed, this goes away. It is because that's how the average is. It's just compute this function, okay, and just average it, right, with large enough number of samples. And you know that for n large enough, the concentrations will say it's going to approximate the integral well enough. And is this function known? Yes. Going back to the measurement, what is this in words? It's saying what is the distribution of measurement given a clean image? x0 is a clean image.
Why did pt of x0, xt go away? You have 1 over n?
Yes, it's just this because I'm okay. Xi,
Sampling about
exactly. I'm sampling instead of doing an integral with this. I'm just sampling I'm sampling n samples from this particular distribution. That's my DDPM box. Okay, and therefore this integral of this thing can be just replaced by a sample average. Is that reasonable? Yeah. Okay. So then, in which case, then in this case, I know sigma t square. I know this function. What is this function? This is in the example, running example is e to the minus y minus a of x0 I whole square. That's what this function is. Okay, that's my by root 2 pi or something like that, or some root 2 pi sigma square, something like that. So I know this function. So I can compute this. Okay, it's a Monte Carlo estimate. Okay, so similarly, I can do a Monte Carlo for the denominator. So let's go back here. Yes, it is expensive. So I'm going to talk about the complexity in a second. I'm just saying, at any particular point in time, if I want to figure out the score, then what will I do? I will start at that point, xt, and then generate n samples, or maybe I can reuse it in the numerator and denominator, whatever. I'll generate order n samples. Then, using those samples are from the correct distribution. Okay? And therefore, I can compute this expectation in the numerator, I can compute this expectation in the denominator, and take the ratio. And therefore, with 2n calls, so how many calls does it take? 2n calls, each for the numerator and denominator, each call requiring t steps of DDPM. Because I have to actually step t time steps. From xt to get to x0, each call will require t time steps. So it's order nt number of steps is needed, okay, for each t. And as t changes from capital T to 0, I have another multiplier of t. So this order nt square number of samples is needed. Does it make sense? I think that's what you're getting to.
This estimator and other estimators just to skip this.
Yes, but you will see the problem with all that, which is that it's going to be biased. In fact, no, that's why I'm going through all this to say, if you want to do exact sampling, I'm just trying to point out various ways of thinking about it and where you're going to hit roadblocks. That's really the point of all these quote-unquote algorithms. Okay, they are algorithms, but are not very scalable. But still, to get a clarity across all this, it's worthwhile to sort of think through all these steps. That's all. Okay. So, but nevertheless, this tells you that in principle, it's possible in order nt square steps. The problem is, what's the dependence on n with dimension? Okay, and it depends on how those function. X, remember, is a vector in d dimensions. So I'm trying to get concentration in d dimensions. So there's going to be some dependence on, and yeah, you will finally hit again the same roadblocks where you're hitting everywhere else. You want to do, because we know there are lower bounds for this problem. Okay, we are trying to solve a particular sampling problem for known hardness results, and that I'll talk about 2 weeks from now. The known hardness results actually is very, very recent. It's a paper by Gupta, Parulekar, Eric Price. So Eric Price, a professor in computer science. It was 2 years back, this paper. So till then, it was not known that it's hard, and it's provably hard is what was shown recently. So therefore, any algorithm you're going to do, either you need to pay an approximation error, or you're going to pay, if you want exact, you are going to have in the worst case, this complexity. Okay? But I'll refine this statement much more 2 weeks from now, saying, is there a smooth analysis? Is there something else we can do? What if I'm allowed a small amount of approximation? All these kinds of things are very interesting questions, and we will talk about some of that. But these are all exact samplers is what I'm talking about right now. Okay.
Show us this derivation.
Now, the rest of today's class, I'm going to derive this, showing that's basically where I'm going to end. Yes, that's basically what I'm going to prove now. But I just wanted to motivate why we are even looking at these equations, because, yeah. Do you have any more questions on this? Yeah.
No.
Okay.
Isn't the proof the same proof as how you derive the Tweezers win? Seems like the score is basically going to be this conditional.
Yeah, but it's a ratio of 2. It's
Base theorems.
let's do the calculation. Yes. Everything comes back to the same thing. There's only Bayes and total probability theorem. There's nothing else in any of these things. That's all there is going on. And yeah, but let's do that. Okay.
And basically you told us that if we knew, thanks to this relationship, we can just do that sum that's at the top, in the bottom that you just scrolled up.
Sorry.
So that's why we're doing it.
Yes, we are doing this because once I have that exact result, then I gave you a way of coming up with a sampler to do it. Draw n samples and then compute these things. They run this thing and then this thing. Yeah, do whatever you want. Yeah, I'm basically telling you how to convert an unconditional sampler to a conditional sampler. Okay, that's all this box is doing. So the first, okay.
Again, all I need to know is that in terms of what I need to be able to do is.
You need to know the measurement operator. Correct, and that is encoded inside this box. Okay, what is the relation between x0 and y goes to the measurement operator. And that's what this is. And note that this method at least doesn't require even A to be back probable. We are not doing any gradient or anything. Okay, it's some box, some translation, reweight it and sample. So this kind of reweighting sampler, even though it looks absurd, it's used a lot. If you think about sort of reward reweighting, what are you doing in RL when you're doing batch-based reward reweighting? Something like this. Essentially, it's a Monte Carlo estimation.
Model is X0. So that's a thing that I'm just using as a black box.
Exactly.
So,
So precisely, and which means that if you have the base policy generating something, you generate a bunch of answers, reweight it, do this, and it's just important sampling. Okay, so so now you can think of various heuristics. How big a batch? Is there something sparsity? There are all these directions you can go off on. But at least I want to go through this formulation to show you where any of this is coming from, just from first principles. That's all. Okay.
And that's not just one block. I don't need to know.
Exactly. This whole point is this all test time. So that's the key thing. Meaning, I give you a single y, and I want to sort of tilt to. I want a sample that's consistent with that y. I can do, if I had infinite amount of computation, I could do all this stuff. Okay. So let's derive this. So we want to derive. So I've written it forward, but I was looking at it. I thought it's good to start from the last line and then get back. Okay. So we want to get an expression for grad log pt of x given y. Well, Bayes' rule says, as you said, there are only two things, total probability theorem and Bayes' rule. There's pretty much nothing else which we are going to use here. Okay. Bayes' rule says that this is nothing but grad log p of y given x plus grad log p of x minus grad log p of y, but the gradient with respect to x. So this goes away. So I just need to figure out an expression for this sum. Okay. So that's why I'm going to do a lot of calculations to get p of y given x. This thing we know already. This is what we need to find an expression for. So let's go back. So I want to get a calculation for grad log p of y given x. So to do that, we'll need an intermediate calculation, which is what we're going to start with. We'll calculate the gradient of the following. What's the gradient of the integral p of y given x, x0, times pt of x0 given xt? Let's start with this. Why is this? Why am I putting this expression up? You'll see that this is what it essentially comes down to. So just bear with me. Let's go through this calculation. You can push this gradient all the way inside because that's where xt is. Okay. So there are three objects here: the clean image, the noisy image, the conditional distribution of the clean image given the noisy image, the conditional distribution of the measurement given the clean image. Okay. So first I can push this all the way in. Okay, grad p, multiply and divide by pt, and then look at this ratio. This is the other. So the other trick that appears in almost all these proofs is the log trick. You've seen this in all these kinds of things. Meaning, whenever you see grad p, somehow get it to be grad log p. And the way you do this is, of course, grad p by p is grad log p. Okay, so you get grad log p times p. Okay, and now grad log p of x0 given x is, now use Bayes' rule. x0 given x is xt given x0 times some normalizing at p star of x0 divided by pt of xt. Okay, so this other term, anyway, I'm going to take gradient with respect to xt, so I don't need to worry about this. So that's why there are only two terms floating around here: the xt given x0 and xt. Okay. Now let's look at this. What is grad of log p of xt given x0 by pt of xt? Okay. Now it's an OU forward process. So which means given x0, xt is just Gaussian noise added to it. It's a noise with center x0. I'm just looking at this. This is, I take an image and I want the density of the noisy image. Just what I've circled in red. Does it make sense? Constantine, you look a little. I'm just doing calculations now. I'm not doing any algorithm. I'm just trying to figure out what is an expression.
If I have the clean image and I need to get a noisy image, I need to run the forward process.
I just need to, yeah, which is the same as adding a Gaussian at appropriate noise level. If I want to get at time t, it is nothing but x0 plus some random variable z with appropriate variance. Do you agree? Which means that the density of xt given x0 is just a Gaussian with that variance and the mean being x0. Agreed? Which means that that's what I'm doing here. And when I take the gradient, the 2 goes away because there's a square. It was first there's a log, so e to the minus the exponent square, the exponent will come down. And when I take the gradient, the 2 goes away. So this is equal to just this. Yeah.
So we don't have a scaling of x0, like xt is some scaling times x0 plus noise, right? In the DDT.
Here, yeah, but this in this case, but that's yeah, but it's finally just some shifted Gaussian. I guess there's some scaling. I'm just ignoring that. Yeah, it depends whether you're using the noise blowing up setting or there are 2 ways of scaling this thing, right? The noise exploding variance versus the variance exploding setting versus variance. So one of those settings, it will work this way. Okay. Otherwise, there'll be some other constant floating around. That's all. But you see that this is just xt minus x0 by sigma square, effectively. The other part is negative log of grad log pt. We'll just leave that alone. So we'll just stick that in here. We'll get py given xt, this one, this quantity from here, times the original density of x0 given xt. Therefore, all we have said is that gradient of p of y given x0 times p of y given x0 times pt of x0 given xt can be written in this form. That's all we have done. Okay. It's just essentially Bayes rule and log trick. That's about it. So now let's get to what we want, which is the gradient of log of p of y given xt. Okay. So gradient of log of p of y given xt. We will use total probability. This probability, we can write it in total probability as the integral of pt of y given xt. I'll condition on anything else I care about, x0, times pt of x0 given xt. Okay. Just total probability. That's all that's going on from this to this. Okay. But now, why, if I give you both x0 and xt, I don't care about xt. Okay. So it's just p of y, y given x0. Okay. And so essentially we are in business almost. So now it's a gradient of the log of this integral, which is nothing but the gradient of 1 over this integral times the gradient of the integral. Okay. And this is exactly what we previously derived an expression for. Substitute that in. Okay. You substitute that in, and okay, let's see what else here. Now the first term is this times that, which is what we have here, divided by the denominator. The second term, this one has no x0 dependence, so it can pop outside the integral, which will give me an inside the integral just 2 terms, y given x0, x0 given xt, that cancels with the denominator. So you just have this thing coming out. So this is what you have. Okay. Therefore, what we have is grad p. So I can take this to the other side. We started with y given xt. There's a minus grad log p. So the sum of these things, grad of p y given xt plus grad of p of xt, can be written as this ratio. Okay. You're wondering where this ratio is coming from. Now you see where it's coming from. Now you just put Bayes rule and you're done. Okay. Good. Now you've seen the proof. There's nothing fancy going on. It's just sort of elementary calculations. And that's it. But it's saying something useful, that you can, if you could sample from something, now you can do it in multiple ways. You can either you can do importance sampling, you can do rejection sampling. All these, there are 3 different methods. Okay, you can do split Gibbs. All this will give you this kind of, if I given a single sample y and I want something consistent with it, we can do all these kinds of things. And these could be useful in some settings. Indeed, people are using this when you want to tilt in sort of some RL type applications. This is effectively what people are doing. Some variant of one of these kinds of things is what is being done. Okay, so we shouldn't just say, just laugh it off and say none of this is useless. I think it's worthwhile to think about any of these kinds of things. Okay, then starting from this, you could use the additional structure of the problem. I mean, these things are only hard in the worst exponential. I mean, the dimension dependence is bad in the worst case. It doesn't mean every instance is hard or bad. If there's some special structure, there are clever things you could do starting from this. But at least now you know what these things are. Okay. You could go a different route. Okay. So yeah, in these several things I talked about so far, they require many calls to the denoising score network, which is expensive. I said in this one it requires order NT squared. I talked through this part when I answered you, but I've written essentially that particular essentially order calculation. N is number of samples, and that is for concentration. So where is N coming in? N is not dimension, N is this. So I want to approximate this. How many samples do I need to approximate the integral well? Okay, X is a vector in RD. So if they're it should at least linear in dimension if the world is amazingly good. And if these functions are nasty, it could be much worse. Okay, it depends on how this P function is. It's an exponentially weighted thing, so something bad could happen potentially there. Right? I mean, it depends on the Lipschitz constant of this function P, for example. Things like that will come in when you're doing, if even with Gaussian concentration, some Lipschitzness will come in when you're doing the reweighted thing. Okay, it depends on any of that stuff. Okay, but you could potentially get away with poly D if your problem is nice enough. And even poly D may be hard for some problems, in which case you may just want to do some local approximation. Maybe I don't care about exactly. Maybe there's some much more structure in these integrals, meaning most of the space doesn't matter. It only matters in some parts of the state space. So
we know that X0 lies on some much lower.
I think in many practical settings, many people here in this room know better than me. I think like tens of samples, just do it and just get on with it. Does anybody know in RL how many samples? If you're doing this kinds of thing in RL, how many samples do you draw to actually do things, to tilt things? You don't. Okay.
For example, if I have a latent representation of X that was much lower dimension,
of course,
I would just.
You could do all that, right? Precisely. I mean, you can use structure to get. I'm just giving you the bare expressions. Now, how you control and now you see where the sample complexity also comes from. How many n is needed to actually get a good approximation of this integral. But there is no free lunch. In the worst case, this rejection sampling, Gibbs sampling, all of them are as bad as each other. But not always, right? Because Gibbs sampling, for example, rejection sampling seems really, I mean, it seems the most obvious way. Just hope for a cat to show up till I sample. At least this is doing something more, okay? That is sort of reweighting things in some maybe a little more intelligent way and so on. But yeah. Okay, so this gives, I think, as far as I know, sort of these are sort of three mainstream ways of doing these things exactly. But now let's shift focus and say, well, suppose I don't want to do this exactly for the image domain. Suppose I want some sort of approximation, okay? Can I somehow do a Taylor's expansion of these kinds of things, drop higher order terms, and do something nice with it? And that brings me to this very popular method called diffusion posterior sampling, DPS, which, given the time, I will stop at this point. I think this is a good place to start. And next week, I'll start with sort of approximation algorithms to do these kinds of things. Thank you.